Hello there everybody. For the course we're doing, the pre-apps, we're just looking at circuit elements, devices like resistor, capacitor and inductor. So what I'm going to do is I'm going to do like 3 lectures, this one on resistors and another one on capacitors, another one on inductors, and in each one I'll set you a wee task or a kind of tutorial thing for it. And there is an IT element to this module. I think it's 2 modules. So, and the IT is like using Word and using being able to research material. So what I'm going to do is get you to do like 3 tutorials on resistors, capacitors, inductors, and then what I want you to do is for the IT part is to do a Word report for me with 3 sections on resistors, capacitors and inductors, and then kind of present that in a Word format. And you, some parts that you might have to research a little bit, maybe find things out about some of the devices there, or components anyway. And so what I'm going to do just now, so there'll be 3 lectures and I'll do 1 on writing reports, and so, but it's not too much work, so hopefully we'll get through that quite quick in the next few weeks. I'll send you like a lecture, I'll send you 3 lectures as soon as I can, but I'm having to prioritise and do other lectures for other courses, so I'll try and squeeze you in when I can. So anyway, so there's, as I say, there's only 3 elements to electrical circuits. And I'm sure you've seen all this before and you've done this with Ian, but I'm just going to kind of go for the start again and kind of revise or brush up on what you know anyway. So we've got our resistor, capacitor and an inductor, and it's quite bizarre to think that out of all the electrical circuits that are in use today, from transmission lines giving us the power to our houses and factories etc, to the computer I'm using just now, is all composed of these 3 basic elements. And if they're not composed of those elements, it's combinations of these 3 elements. For instance, computer memory is generally composed of a capacitance, and that can hold on to a charge indefinitely. In some cases it can hold up to charge for months, even years, as long as it's isolated properly. And that's how the computers can remember, have a memory basically, remember code and stuff. Inductors have their own certain properties, and resistors we're just about to talk about. Okay, so what is resistance? So before we talk about resistance, we want to talk about what is flow of current, about electrical current. How do we think about that? What is that? If you have a material that's conductive, imagine that's its atom, something like copper or something like that. Copper is quite a good conductor of electricity, and the reason being for that is the electrons that are furthest away from the nucleus and the copper, that type of atom, they're kind of loosely held by the nucleus. Imagine, obviously the nucleus is positively charged and the electrons are negatively charged, so these electrons are attracted towards the nucleus and that kind of holds them there. But in some materials that are quite loose, like in metals and conductors, and they can easily, say I had another atom here, if you find that the electrons can easily jump from one atom to another, and that's how they kind of travel or conduct along the material. In an insulator, the electrons are held very tightly and it's very hard for them to move. And not only that, insulators, like say wood, is composed of different elements to make a molecule. So even if you do have so you've got a molecule, something like that, and you do have molecules that could conduct. Maybe this one can conduct okay and this one, but it's surrounded by atoms or elements that don't conduct. So it's harder for that material to conduct. So they called it insulate because it insulates against conduction. When saying that as well, you'll find that materials that conduct electricity tend to conduct heat as well, like metal. You can, if you put a fork or a metal stove, the handle gets hot. And that's why some of them will have woods around it, because wood doesn't conduct heat as well as electricity. That's another story. Excuse me. Now, so generally what we'd have is, say, a wire, and if we apply a force, so see, what happens is we apply a voltage across here, and what happens is any kind of electrons that are loosely bound to the nucleus. I'll have to do this. So I'll go into the flow of the convention of electricity in just a little second. So see, that was minus and that's plus. If you get two magnets together and you get them on the same polarity, in other words, it's like having the same charge. If you try and push them together, they try and repel each other. It's the same kind of phenomenon or thing happens here, where if you apply a voltage across here, and this is negatively charged here, this will push these electrons in that direction, and this here will pull them in that direction. And that's how you get the flow of electrons, and that's denoted with I as in current. So V for voltage, I for the amount of current you get. And now you'll all have seen this Ohm's law, V equals I R. It's always written like that, and I think that can actually be a little bit deceptive, because the flow of electricity, this kind of implies that you get a voltage because you've got a current multiplied by this resistance. But that really isn't really what's happening. What's happening here is you have a current and a voltage divided by the resistance. So the current is a manifestation of the voltage and resistance rather than the voltage being a manifestation of current times resistance, because the current is determined by the voltage ultimately. And so if you have so also it's determined by how much resistance we have to the electricity flowing in this direction. And the resistance, well, is determined by the type of material it is and by the cross-sectional area of the wire. It's just like if you're trying to push water down a water pipe, if you've got a bigger pipe, you're going to get more water's going to go down it. It's that exact same principle. It's about volume and space, and this is the pulling power, or the pushing power is the voltage. And so, for instance, say this was attached to a battery, and it is an odd thing, mind you, that before they discovered what electrons were, they knew what was happening with electrical circuits, and they did think it went from positive to negative, and it wasn't till much later they realised what was actually electrons, and they were actually going in the other direction. So you'll find the convention of flow goes from positive to negative, but it's actually electrons that are moving around in this way, and that's the cathode and that's the anode, if you know what I mean. So there we go. And so if we, let's see, right, so looking at this circuit here, I'm thinking about V equals IR, then rearranging that to find out what I is. So let's see if you can see that. V equals IR. If I divide that by R and divide that by R, I equals voltage divided by resistance. So let's work out what the current is going to be here. I equals V over R, which is going to equal 12 volts divided by 6, which equals 2 amps. I'm sure you must have done this before, but I'm just kind of reiterating that. And also, if for instance you had another 6 ohm resistor and you decided to add that to the circuit, and this is what you would call a circuit that has resistors in series. I'll write that down there. Series. And if this was, say, another 6 ohm resistor, we'd have to recalculate the current. So let's see, the current would equal the voltage, which is 12, divided by the resistance. Now in this instance here, in a series circuit, the resistance is the sum of these. What they mean is just add them together, and that will give you the resistance, the total combined resistance. Then if they take a different pathway, I'll show this in a wee minute, you get a different type of circuit where it does change things. And so that would be R1, so that was R1 and R2, so R1 plus R2 is going to be 12 over 12, which equals 1 amp. That's supposed to be a 1. Right, so with a 6 ohm resistor, you got 2 amps, and if you double the resistance, you get half the current with the same voltage. And what we could do as well here then, say we put another battery on here, and by the way, this is a battery, the symbol for a battery, and it is a direct current. In other words, the current goes round that circuit in one way, it only goes one way and one way only. So again, we decide to add a battery, and we'll say we add a 24 volt battery here. Now what do you think I'll do to the voltage? The voltage, you would just add these voltages together. You get a thing where you get current laws and voltage laws and these types of things. And this one, and these, what you would do is you just add the voltages together in a circuit. Depending on what way they were going, if this was wired up back the way, you would have to subtract the voltages from there, but we'll get to that. I don't think you really need to know that for this course, but anyway, or to be able to get access on it. So say that was 24 volts. So what's the new current going to be with the 12? So the current is going to be the voltage, which is now 36, divided by 12, 12, that's going to be 3 amps. So you can see that's how you work out the current that can flow. Depends on the voltage and it depends on the resistance. That tells you that. Let's see. Now, if you were to wire this circuit up, so it kind of looks like that. You see that again was the 6 volts, and this is your 6 ohms, and this is 6 ohms. We'll call that R1 and R2. What happens in this situation, the current that's going up here is going to split down here and down there. And if they've got an equal resistance, what's going to happen here is they're going to allow an equal amount of current to go down both these branches, and then it's going to recombine here, and the value of this current is the same as this value of this current. It's like if you've got a tube and you put a certain amount of water on one side, you're going to get the same amount of water coming out the other side, no matter what happens. So, but if you had a hose pipe that split into two, like that, and they were of equal size, you would get an equal share of the water going down there, an equal share of the water going down there, and if you recombined them like that, you would get the same amount of water that went in there that comes out there. And that's kind of what's happening here. What we have to do is work out what would be the total resistance of that. In the series circuit, this is called a parallel. Parallel circuit, and we have to figure out a way of finding out what the current would be in this whole circuit. And so I'll just tell you the kind of shortcut for this. So 1 over RP, and we'll call it RP because that's R parallel. Another one, the series one, I'll call it RS. Always try and use what you're denoting, what you're looking at, or the variable you're looking at. Try and make it clear of what you're doing when you're doing your calculations. It's easier to see what's happening. So in other words, that's what I'm saying. I'm calling this RP because it's parallel. That one I call RS, just to distinguish between them. But what has been found through experimentation, and we figured out that this is how you would add these two resistances in parallel. And there's a wee mathematical trick to this called cross multiplication. And so you can, if you've only got two resistors there in parallel, you can use this wee shortcut, which would be R1 times R2 over R1 plus R2. In fact, I'll show you how you get that. And cross multiplication in fractions would be R2 plus, so this would, you multiply this, R2, and cross multiply with this one, with R plus R1 over R1 times R2. And because that's 1 over RP, if we're wanting RP, we flip that over. So you get RP equals R1 times R2 over R1 plus R2. Okay? I hope you can see that and you understand that. So if we're working out what the two 6 ohm resistors are going to be, so RP is going to equal 6 times 6 divided by, 6 plus 6. So that's going to be 36 over 12, that's going to be 3 ohms. Now it's quite odd. It's quite odd to think that you've got two 6 ohm resistors, but because they're in parallel, the combined resistance is much lower. It's because they've got two paths to go. And so, well, so we can just use that. We can say it's equivalent resistance. We could in fact just replace this with one resistor there and say that's 3 ohms. Hope you can see what I'm doing there. And then, so we've worked that out. So we want to work out the current for this one is going to be 6 volts divided by 3 ohms, which is 2 amps. Excellent. Right, so that's how you combine parallel and series resistors together. Let's have another quick look at say we had one like this. And of course, see that's 10 ohms, see this is 5 ohms, and see this is 2 ohms. And we want to work out the current going through the whole circuit. And see this is a 24 volt battery. And so the first thing we want to do is find out what its equivalent resistance would be. Equivalent resistance. So the first part we want to look at is this parallel part here. And using the equation we looked at before, RP equals 5 times 2 over 5 plus 2. 5 times 2 over 5 plus 2, which is 10 over 7. Which is something 1.33, I think. See that? 1.33 we'll call it. I've not got my calculator on my phone on me, so, and that's in ohms. Now, what we can do then is replace that with that, and that's 1.33 ohms. And then all we need to do is add these together. So essentially what we could really do is replace this with one resistor. You're not doing this in real life, but you're kind of doing it on paper and in your head. This is where you're kind of looking at what's happening. And that's 11.33 ohms. So we want to find out what the current is. So the current would be 24 volts divided by 11.33 ohms. So see, I've not got my calculator. That's nearly 12, so that'll be it'll be just over 2.1 or 2.05 amps or so. Be round about that. So that's how you add resistances together in series and parallel, and how that you can work out the current from that. Right, so what do we use resistors for? Well, resistors are needed when we want to regulate a certain amount of current that needs to go through a circuit. For instance, say you had 10 volts battery and you wanted to get 10 milliamps out of that. 10 milliamps is 10,000th of an amp. And you can generally, when you're writing it in maths and doing it, you're calculating things, you tend to write it like that: 10 times 10 to the minus 3. What that means is 10 to the minus 3 that equals 1 over 1000. So in other words, if you multiply something by 10 to the minus 3, it's like dividing it by 1000. So that's kind of like that. 10 milliamps divided by 1000 would give you how many amps it is. Anyway, so 10 milliamps is like 10,000th of a milliamp. Right, so that kind of gives us a clue to what size of resistor we need for this. If we've got a 10 volt supply, we need 10 milliamps. So if we put V equals IR, and we're wanting to find the resistance that we need to get this, so 10 volts divided by 10, oops, minus 3 amps, and that is going to give us a value of 1000 ohms. Oops. So it's just a bit odd writing this because I'm starting to stretch over. And when I look at the screen, I don't know if I said, but it's all back to, it's like a mirror image, so it's back to front looking there. It's quite odd at times. So if you've got a 10 volt battery, we need 10 milliamps. We need to use a 1000 ohm resistor, and you would look that up in your wee chart with the coloured bands around your resistor, and you'll have 3 bands there. And for this one, 1000, I've looked it up as brown, black and red, and then you get another band here that tells you your tolerance, which is basically the quality of your resistor. If it says it's 1000 ohms, if it's gold there, that means it's plus or minus 5%. So it could be 1050 or 9950 or somewhere in between there. So it is prudent, if you're making a circuit, a wee hobby circuit or something, just to test them out to see exactly what they are, just so you know if you're using a transistor, you're getting the right gain and stuff. So that's a wee basic intro on what we need for. I mean, what else do we use resistors for? I mean, we use the properties of resistance for like fuses, and if you think what happens, see if you've got a wire like that and you've got all these wee atoms in there that can conduct, and this is a certain area here, cross-sectional area it's called, that's the area. Now if you try to force too many electrons into there, you get like a kind of bottleneck and a build up of electrons, and they're moving. Electrons are moving. And what happens if you get things moved? It creates heat. So it's kind of like the kinetic energy of its motion is changed into heat, and that's why wires will, if there's too much current or over current going through a wire, it will heat up because of the friction. It's a bit bizarre thing. Do you know that most of the energy in the universe is actually motion? If you move on from this and you end up doing like thermodynamics and things, you'll find that an expression of the heat, so I think, or the energy contained in a material is called its entropy. It's quite a hard thing to get in your head, but it's all kind of connected with motion. Like a gas with particles all moving about has got more entropy than a solid that's not got that much moving about, and it's all to do with the heat created. It's quite mind-boggling. But so what happens anyway, and this will end up heating up, and it gets to the point where the material starts to melt, and then it will just snap, and obviously that will break the circuit. And what you do is you work out, you say, right, I'll make sure that can take 13 amps, up to 13 amps. Generally, if you're using a 13 amp fuse, you wouldn't want to be going more than 10 amps. Because, and also, with the wee metal fuse, the cartridge fuses, it takes a little while for it to melt through. So if you get a shock from that, it might still kill you even though it's fused and kind of protected. It takes a little bit of time for that to melt, whereas magnetically tripped breakers do it instantly. They're much safer. But these aren't really for that, these are there to protect your equipment and stuff really. So now, so that's that. What else can I say about that? So obviously if you've got a bigger cable, a bigger surface area, you can get more electrons into there. So that's got much less resistance than the wee thin cable. And you'll have seen the cartridge fuses, wee things like that, and you can see the wee wire in the middle. Then you get other fuses for electric vehicles and stuff, where you get a really high currents, maybe 60-80 amps in an electric vehicle, where the element in there looks like a ladder actually, and it's covered with a kind of powder, a silicate powder, and that absorbs all the sparking. Whenever you break a circuit, especially one that's got any kind of capacitance or inductance in it, what I mean by breaking a circuit, even just opening a switch, you'll get arcing and sparks will occur between the 2 points of where the switch meets and doesn't meet. When you open it, it opens. You'll get sparks and things will occur across there. Because if it's an inductive or a capacitive circuit, you will have magnetic fields and electric fields that are already established and created, and when you switch off the power, they go, oh, and they want to try and they just kind of decompose and decay, and it leaves all this energy that's bunging about the cables, and it's trying to do something, and it picks the easiest path. So when you unswitch something, the easiest path is when that's just apart from it. So you get arcs and sparks. It wears out your switches and wears out things, and you have to replace them. So a lot of times you'll use actually transistors as switches, which don't actually have any metal parts that connect. A lot of times, like in relays, not in relays, but the contactors and things, if the metal touches other metal and there's too much current going through it, will actually weld together because of the heat, and they can't actually pull it apart. I was doing an experiment at uni in the 4th and 5th year, and we had a contactor as an extra safety precaution in the circuit, because we're looking at electric vehicles, and sometimes it's like 120 amps, and it only takes a 20th of 1 amp to kill you, by the way. And so we had this contactor, but this, what had happened is we had a short circuit, which meant there was a massive current went through this, and this contactor had welded together. So this circuit part of the circuit was live, and we didn't know it was live because the contactor was, even though we'd switched it off, it hadn't moved, it just stuck. And it was my professor that noticed it. He says, well, that's still on. I was like, what? Because we were mucking about with it. Very dangerous. And so, fuses, and different sizes depending on what operation they're getting used for. What else? Right, we'll maybe go through a wee thing where, say we've got an LED, right, here's a good one. If you try to regulate what's going through an LED, a diode LED. LEDs are pretty cool. It's when the current goes through it. I don't know if you've done physics in 5th year, and possibly 4th year maybe. You've done a thing called Planck's constant, and that's the amount of energy you need to release a light photon from an electron energy level, depending on the wavelength, depends on the light that comes off it. Excuse me. And but anyway, say this is a 3 volt and you only want 0.02 amps to go through that, and say we wired this up to a circuit. If we didn't have a resistor there, and say this was 12 volts, if we didn't have a resistor there, I don't know if you've ever done this with Ian or whatever, the LED will just blow up basically. So because it's only, you can't put too much, because they're very sensitive, these wee things. They're wee sensitive things, you know. So anyway, now what we've got to do is work out what size of resistor we need to safely ensure that we can work this. So one thing I've maybe not explained, but I'm kind of expecting you to know a bit about this beforehand, but you get a thing where you get your Kirchhoff's voltage law, where if you've got 12 volts there supplying the whole circuit, and you're needing 3 volts is going to get taken off of this, that means you're going to have 9 volts left for here. In other words, what that means is the supply voltage is distributed between whatever devices or elements are in your circuit. So if that's taking 3, that has to be taking 9. So there we go then. So basically, let's see. So the resistance here is going to be equal, well, so V equals IR. Again, we'll rearrange it, divide that by I, that means you have to divide that by I. So you get V over I. Now, I don't know how much maths you've done on things, but one thing to remember when you're transposing anything that's got an equal sign, you must do what you do to the one side to do the other side. So if you do one thing to the left hand side, you have to do it to the right hand side. And that's basically what I did there when I had V equals IR. I divided that by I and divided that by I. And they cancel each other out. See that, and you're left with the R. Anyway, so let's see. The voltage here, so it's 9 volts divided by the current that we need. So if whatever we make this resistance and everything to be, you'll get a current that will flow through the whole circuit, and we want it limited at 0.02 amps. So let's see, 0.02. So I think that's going to be 1800 ohms. I think 92. I think so. I'll just check that. Might be wrong. I should try our best to get into the habit of not just relying on your calculator to make calculations. Try and use that thing up there as much as you can. Keeps it busy. See, I'm away with it. Lucky I do have things to check this with. So that's 450 ohms. According to this. $450 ohms. So that's the resistor you need to make sure that's got 0.02 amps and 3 volts. Good stuff. Now, what else do we need to look at here? can maybe look at, let's see. Right, so I suppose you could put that down as a kind of equation, I suppose. You could say that resistance required to light the LED is power source voltage, take away the LED voltage. This, I swear there, I'll write it over here about it. On it, room here, that's the recording. So resistance needed is equal to the power source voltage minus the LED voltage and divided by the required LED current. So we could test that out then. Say, I don't know, say we had, again, say we had the same LED, right? And for instance, say we had, say it was 140 volts, say. Right. So what would that be then? The power source minus the LED voltage, that's 3 volts. So that's going to be 140 minus 3 divided by 0.02. And what's that going to work out at? Let's see. So 6850. So you need a much bigger resistor there than the last one because there's much higher voltage. Yeah, so that would be 6850. So, excellent. Well, there's something else. I'm just going to quickly look at something else here, actually. And what I'm going to do is I'm going to put this all in a wee document for resistors. I've given you a little one before that, and I'm going to give you a tutorial with it and get you to do that as soon as, and that will make up the first part of your report actually. I'll give you more guidance on that in the next week or two. What was I going to look at here? I'm just going to quickly rattle into it. Power is equal to the current times the voltage. That's one of these things you could become an electrician or an engineer. That's like V equals IR and power equals IV. It's one of these things where you'll know it that well that when you're 85 and there's marbles rolling about and you can't remember your kids' names and stuff like that, you'll still be able to remember this. Like, you'll just rattle that out. And they'll be like, oh yeah, V equals IR, definitely. Now, because we've got V equals IR there, right? And so if we replace this I with, so say I equals V over R. If we replace that I with that, that's going to be V over R times V, which is V squared over the resistance. That tells you the power. Now, if you're using those tiny wee resistors that you get for hobbies and at the college and stuff, that put in the wee pencil box things, they're fine for very low currents and stuff like that. And because they have a kind of power rating, and generally a wee hobby one like that would be about probably 0.25 watts. If you think there's going to be more power in your circuit than that, you have to get more robust resistors which can handle a bigger current. Now let's see if this would work then. See, that was 1.25 watts. I wonder if that would work. So looking at this then, so we're saying power equals V squared over R. Alright, so that would be 100, because that was 140 and that was minus 3. So the available power to the resistor is the voltage that's across the resistor less, well, the voltage that's across, so it's the source voltage less that, so it'll be 137 squared divided by this resistor here, 6850. It's not looking too good for a resistor, I don't think. Let's have a look here. It'll probably melt or something like that, or blow up. Hopefully, it'll be pretty. It's nothing like a big wee explosion again just to waken you up in class. Yeah. So 137. Yep, 2.74 watts. And watts is the unit for power. A watt is a joule per second. A joule being the unit of energy, and power tells you how much energy you've used up every second. So anyway, that's 2.78 watts. So that's 2.74 watts every second. But that can only actually handle 0.25 watts. So that's going to break down very quickly. Yeah, I'm just trying to think. So is there anything? If there's anything else, I'm trying to think. I know it's just been a crash bang wallop with this. But from this I want to take away with resistors. Another thing, see when you're looking at circuits, what we do is we tend to disregard the resistance of the wire, just when we do calculations in the class and stuff. In real life you have to take this into account. Like when you're wiring up a house, you get your R1 and R2, you have to work out where your earth fault loop impedance is, all these kind of things. Your CPC, circuit protective conductor. I'm trying to think what else. Aye, so we tend to disregard that, but in real life you don't. When you're transmitting electricity from Edinburgh to London or whatever, the amount of losses you get from the cables are very high, or can be high. And maybe talk about sorry, I've just so aye, what else? What are they made of, resistors? I want you to find out for me, please. I want you to pick 3 different resistors, and I want you to tell me, in maybe just a kind of paragraph, 2 or 3 properties, or 2 different things, 3 different things about resistors. Say what they are, what they're used for, and what makes them. There you go. And 3 different types of resistors. I want you to find that out for me, and that'll be part of your kind of your IT thing, your researching. And I'm going to send you a little tutorial that'll have a couple of questions, maybe an LED one with a circuit, and I'll get you to do a parallel and a series circuit. And can't really think of anything else just now. But whatever I've forgotten in this one, I'll put in the next one, and we'll look at capacitors. Okay, as I say, we'll do capacitors, then inductors, then I'll do another wee lecture on writing a report and how to make it look presentable. And I hope everybody's holding up well with this isolation. Hopefully not too long now, a couple of weeks, and as the goonies say, never say die. Okay, take care now, speak to you later.